Okay, so what does that mean really? I mean, how do you know that? Let me just digress a little bit. So if you're looking at a semiconductor, right? So you show some energy here, you plot some energy, and you plot some density of state, right? And what you got sometimes that you have a rising edge, right? And then level, and then some peak like this. And this little rising edge, what is this edge? This is known as the Fermi edge, Fermi level that you see. Okay, and so that's nice. So you're looking at silicon. This Fermi level, this edge usually occur around 1 eV. The sudden rise in energy, in density or intensity of the electron. If you're looking at surface, you would see that, okay, well, you're starting to see a little bit of peak below this thing, okay? And you can very easily find them because they are below your Fermi edge, and these are known as surface states. They only occur if you have a surface, which is most material, because every material has a surface. So they are usually very weak by comparison to the bulk. Why? Because if you're looking at bulk material, right, not nano object, you can calculate the surface atom, amount of surface atom to amount of bulk material ratio, and you find this ratio to be rather small, and thus contribute to the small intensity that you see with the surface states. But in certain direction, you can find these surface states, and we'll talk a little bit about that when we talk about for the emission material. Okay, so this gives rise to the electronic state lying within the band gap of the bulk, so that's the signature. And the energy of distribution of this surface state depends on several things. It depends on the surface potential, is electrostatic, usually electrostatic potential. It depends on the crystal structure itself, right? Obviously, the physical structure could affect how the surface state is distributed, because after all, you generate your electronic structure from the arrangement of periodicity on your surface. It, of course, depending on the nature of your surface itself, what kind of chemical composition that you have. If you're talking about pure surface, pure material, then silicon versus germanium, of course, they would have different surface state. They would look different. You can also have absorbate, right? We talked about absorbate early on. If you absorb on the surface, they would change your surface state as well. Okay. So surface state generated by foreign atom are known as extrinsic. So this is terminology. When you read literature, you see some of these words coming in. Extrinsic state, while those correspond to clean native surface are intrinsic. So you have intrinsic state or extrinsic state. So if you are looking at clean material like clean silicon, clean germanium, you find this surface state, right, like this. On there, they are intrinsic surface state. And then if you put some material absorbing on top, you'll see extrinsic state. Okay, so and one thing about these is that so here I try to illustrate that one of the things about electronic structure is that depends on surface potential. One of the things that come to mind, of course, when you have a material is the work function. The work function, you can think of it as the energy required to take an electron out to the vacuum level, to the continuum. Okay? So it's kind of like the energy gap before the energy you need to kick the electron out, to make it into a free electron, right? So here, if your electron lying below the Fermi edge, right, we are talking about a metal. So metal, all the electrons are filled to the energy level defined by the Fermi level, right? So below, you have all the electrons trapped inside, and now you just you ask the question, how much energy, minimum amount of energy do I need to remove one electron to make it into a free electron? Okay, and that energy is called a work function. Okay, so the picture is that this Fermi level is below, so this is energy 0. So this is negative, right? right? So this is E here like that, and so once you kick it above 0, you would have kinetic energy of this electron become free, and this difference is known as the work function. And this work function, of course, related to the surface potential. So different material will have different work function, and it indirectly related, of course, to the chemical, to the nature of your material, silicon and germanium with different work function, and from lithium and so forth. Right? Crystal structure dependence. Here's an example. Here you have a complex structure. Gallium arsenide, interesting material because in the late 70s, early 80s, solid state laser was created with gallium arsenide, and because of the direct band gap, we'll talk a little bit about that direct band gap. And so here you have a gallium arsenide, arsenic, gallium. They are arranged in a diamond structure, just like in different position of diamond.